Hello, everybody. Good day and welcome to session 3 of the workshop series on thermal simulations. My name is Sam, and I'm going to talk more about myself in a short time now. Before we jump into the session, I would like to check the GoToWebinar application if everyone is able to hear me. So, there is a small raise your hand button on the right side corner of your application. So, please press that button if you're able to hear me. Okay, I see many hands coming up. Excellent. So most of you are able to hear me. So if you have some audio issues during the course of the webinar, then please check your settings in the application, or you could even call to the toll-free number mentioned in the email which you received. So now you can, you can put your hands down and then we can start the session. Okay, the workshop session, this is the third session and the last one of this series. A quick recap on the previous sessions. The first one was on the basics of heat transfer. So basically, the conduction, convection, and radiation effects, a short description on what these are with example simulations, and a quick post processing to differentiate between the conduction, convection, and radiation effects. The second one was a dedicated session for conduction, the application of conduction in the field of industries and so on. So it was hosted by my colleague Mr. Ahmed. I hope you liked it. And this is the third and last session, which will have its focus on convection. And to be in particular, it is in the cooling of electronic devices. For your information, we record this session and it would be uploaded to YouTube and published to our forum latest by tomorrow. You will also receive email notifications regarding the same. So I have planned a schedule for the next 1 hour in which I'll be uh, giving a brief discussion, having a brief discussion on what is convection and its role in industrial applications. About myself, my name is Sam Prabhu Jesu Rajendran. It's quite a big name, so you could refer me as Sam in any of the mail and forum correspondences. I basically have a mechanical engineering background with a specialization in computer aided engineering, especially in CFD, FEM, and rigid body dynamics. So it's multi body dynamics. Uh, I have a master degree from RWTH Aachen University here in Germany, and I've quite some experiences working with multi-phase flow, phase change modeling, and many other fluid flow simulations with regard to the computational fluid dynamics stream. And with regard to structural mechanics, I've done material modeling of a material called as aerogels. At SimScale, I do a variety of tasks. So primarily, it is going to be support and service. So if you have submitted any query to SimScale through any of the channels, then you probably expect a reply from me. And this is the agenda for today's session. So to start with, what is SimScale all about? So why should you simulate something in the first place? Why should you use SimScale to simulate? And a description, a short list of all the features which are offered by SimScale, like the fluid simulations, structural simulations, and any other features. And then we go into the topic, basically the types of convection. We have many types like the natural convection, forced convection, gravitational granular convection, and so on. And we would see how convection affects or helps in various electronic devices with a small case study and some design variants in it as well. Then we would see how this could be simulated in SimScale. So we call it the 3-step process, how this is going to be done. And for today's session, we have two convective heat transfer simulation setup, which I will be showing a live demonstration on to set up the case. And then we would look into some interesting results out of them. So, like, say, streamlines and slices across the domain to see how the contours vary and make some comparisons, do some improvements in the design, and see how we could get an optimum result out of convective heat transfer. Finally, we would have a Q&A session. So you can already start typing your questions on the question panel. I'll try to cover most of them at the end of the session or whenever something interesting comes up. And from the number of attendees, I see that the number is so high, so I might not be able to answer all your queries here. I'll try to cover most of them, and probably the most important ones or the most common ones which many of you have queries with. Uh, if I'm not able to answer your queries within this time period, you could anytime post your queries to the forum. It's a place for all your questions, and you have experts and power users to answer your questions. And a quick information on the forum. So we have the SimScale forum, and we have a dedicated page for this session, and you can just start typing your queries, or even if you have an interesting problem statement, then you can just tell us the problem statement and we can help you setting it up. A quick note is it would be a better option to put your queries on the forum because most of them have the common doubts, and it saves time for everyone. And now, a short note on who we are. SimScale is an online simulation platform which is completely based on cloud. So all your model setup for numerical computation probably is being solved based on our cloud computing capabilities. So you don't need to have any prerequisites except from having a browser. To start with, why should people actually simulate? So a design process traditionally followed is in this way as shown. So you start with the design and then create a physical prototype. Then we test the prototype, do design changes, and then again, based on the changes and the results, we again continue this process iterative. Uh, Again, go to prototype, testing, design changes, and this keeps on going. Creating a part physically involves a lot of human and machine work, and it consumes a lot of time and money. So this is where simulation comes into play. You do the physical prototyping and testing together in simulation. So you could say it as a replacement maybe. Simulation is easy, fast, and cost efficient in order to achieve the design cycles. And we can also test some what if scenarios to see how things work. And now, why SimScale? So basically, simulation is necessary for any of the design process. And now, why should you use SimScale? There are three basic things: the accessibility, cost, efficiency, and the availability for everyone. You don't need a high performance, say a RAM or a graphic card or any other hardware or software for that matter, in order to perform simulations using SimScale. You should just have a PC or a laptop with a browser installed in it. Yeah, and then you're good to go. You can perform high performance computing on your on our cloud-based platform. All you need is an interesting idea with a CAD model, of course, and a basic knowledge to set up the simulation. Actually, even if you have an interesting idea and then you can let us know, then we would be happy to help you to get through the simulation. And then going to cost efficiency. So basically, SimScale is free to use. So the concept of public projects and private projects are there in SimScale. Basically, you can sign up for free and get access to use up to 3000 core hours with public project usage. So this is a free community account. And then if you pay for it, you have the access possibility to have a private account with a dedicated support. So you pay for what you use and how many core hours is being used. So that is how we tell it as scale on demand. And then for everyone, we have a crowdsourced library. So it's a lot of public projects. I could quickly show you the public projects. So this is a list of all the public projects we have. In principle, we have close to 15,000 public projects. A lot of them, say for example, you have for multi-phase flow, from filling the concrete, or wind turbine, server room cooling, starting from finite element to computational fluid dynamics. You have a variety of simulations which are carried out earlier by SimScale team as well as the community users, and because of their contribution we have a whole lot of templates. So if you just have an interesting idea, you could just quickly go through this page for any of the template projects which are existing on our platform. So if there are any existing projects, you could just make a copy of it and put your own geometry. That is also possible, or that could be a starting point for setting up your own simulation from scratch. And now, what are the fluid flow simulations possible using SimScale? And since today our session is going to be on fluid flow, that is convection, so the fluid flow simulation possible are incompressible and compressible flow simulations, convective heat transfer, multi-phase flow, and so on. There are a lot of types, and our area of interest for today is the convective heat transfer. One other interesting heat transfer application would be the conjugate heat transfer analysis type, wherein we have both the solid and fluid domains considered for the simulation setup. But in our case, for convective heat transfer, we would only have the fluid domain modeled and then analyzing only the fluid domain. We also have some advanced applications like the rotary machinery, the porous media, which could actually be clubbed with any of the previous analysis types. Say, for example, the porous media could be implemented in an incompressible flow solver, or a 6 degree of freedom motion could be incorporated in multi-phase flow. So maybe a ship. So for analyzing a ship flow, it is air and water, and then it becomes a multi-phase, and ship would have a 6 degree of freedom motion. So this is a typical example of using the advanced applications in the basic fluid analysis types. The solver which we use for fluid flow simulations are OpenFOAM and SU2, both of which are open source solvers available online to everyone. So we use these codes, try to put in a graphical user interface, and then incorporate our own specific ideas into this in SimScale platform. From the point of view of structural mechanics and the other simulations, we have static analysis, dynamic analysis, frequency harmonic, modal analysis, and so on. With respect to finite element simulations, and the other types, we have particle analysis, things which could be also of interest to you. So let's now dive into the topic. What is convection? So we would see what is convection, its types, its industrial applications, and so on. So, a quick introduction. I believe some of you would have attended my first webinar session on in the series, which was the basics of the heat transfer phenomenon, and in which I discussed about convection. So, convection is one where the heat transfer is achieved by particle movement. So, it is basically a characteristic of fluids, that is liquid and gases. And a quick example is, say, during winter, you feel cold because of convection, because the air around you removes heat from your body. So this is done naturally, and this is what we call as a natural convection. This is a simple example. So we have two types of convection in general. One is the passive or natural convection, and the other one is active or what we call it to be the forced convection. So to start with the natural convection, the natural convection takes place with no external sources. So this is basically going to be a buoyancy driven flow, say due to gravity maybe, and this is caused due to difference in density because of the temperature changes or pressure changes. So we know that the density decreases as temperature increases. That is, the lighter fluid, which has a higher temperature, tends to rise up, and the colder air, which is at a lower temperature, tends to come down. This essentially forms something called a convection current, which is a bulk movement of fluid. So during natural convection phenomenon, hot air actually moves upward as plumes. This is given in terms of a specific number in scientific terminologies and notation. We call it in terms of the Rayleigh number. The Rayleigh number is a product of the Grashof number and Prandtl number. I know it is like too many terms, so we would just split up into easy ways. So the Rayleigh number is nothing but it is something related to the buoyancy of the fluid and the viscosity. So the momentum diffusivity is nothing but the kinematic viscosity and the thermal diffusivity. So in principle, you can see from the images on the right that this is a typical example of a heater. So the hot air tends to move up and the cold air tends to come down. So you could also see this principle in liquids. Say when heating of water, when the bottom surface of the water is heated up, it tends to move up and the top surface comes down. And now we go on to the next one. The second type is the forced convection. The forced convection is one where the fluid movement is obtained by external applications and sources, say for example a fan, a pump, or etc. So this enables increased rate of heat exchange. So as I told you earlier, during winter we experience something called the natural convection. We could feel the temperature difference during natural convection, and this could be artificially imposed into a system, and this is what we call as forced convection. And forced convection actually brings much more temperature difference than natural convection, as in we could get the required heat transfer which we expect from any system using a forced convection. Just like Reynolds number for the passive case, we have the Peclic number for the active one, where the Peclic number is given by the heat transfer by advection by diffusion. So advection is something like particle movement in bulk or bulk movement of the fluid, and diffusion would be in particle level. And then we have something called the mixed convection. To quickly say an example on active convection, so we have the heat exchanger, where you have a cold water going through one of them and hot water going through the other end of the pipe. So you have the inner fluid and the outer fluid. So heat transfer takes place from the outer to inner fluid using a convection. So on these surfaces, convection takes place, because of which you force the cold fluid to become hot at the other end. This would be a typical example of a forced convection. There's something called the mixed convection. Uh, this is to get the difference between the natural and forced convection. So we have the external forces and the internal viscous forces. So based on specific term called Archimedes number, we decide it is going to be, or which effect is going to be predominant. So in case if the Archimedes number is much greater than 1, that means that the effect of external forces are much greater than the internal forces, then it is going to be the natural convection, and it's the vice versa for the other case. So we have the oven as an example where convection takes place, or any of the electronic devices. Usually they have the fan in order to bring about convection in the system. We now go into the industrial applications. So basically, cooling of electronics is our topic for today. How does convection help in electronics? As in, every electronic device usually generate heat, and it is really important to have a proper thermal management for optimum operation of the device. For low heat generation applications, say for example like the routers or LEDs, natural convection would be of help. So we do not need to have any external uh, sources to aid in the convection or removing the heat. But for high energy devices, like for servers or computers, we require a forced convection to remove the heat from the system. In this case, on the right hand side, you could see small multiple fans over here, which aids in the convection process. And in a server room, this is an image of the data center. So this is how the cooling system works, because the servers are heated to a large extent, and in order to maintain the server rooms in a better condition, we need to remove the heat from the room. And we have vents on the tiles from which cold air is let into the room, and then they try to remove the heat from the system. So you see the blue ones which comes in, and the red ones are the heated air which is being removed from the room. So how does CFD help? So we could obtain a 3D distribution of the flow and temperature, check for hot spots and avoid recirculations and stagnant regions. By this way, we learn how heat transfer take place, and heat is removed in an efficient way by designing and positioning the uh, input force or input source in a right position. We could also test some what if scenarios, and this is the case under consideration. So a Raspberry Pi board is a series of single board computers, essentially the size of our credit card. As you can see here, this is a board, the Raspberry Pi, and you have the CPU, we have the GPU, which is the graphical processor unit, and you have many other devices. And on the right hand side, you could see a model created using one of the CAD softwares. This is the CPU, and the red blocks are CPU and the GPU. We have some vents which could aid in natural convection, and we also have another vent which could help in forced convection. And now for the design variants. So we consider two different variants, and for the first one of natural convection, air comes in and goes out through these vents. So the inlet air is controlled at a particular temperature of 293 Kelvin, which is the room temperature, and the outlet is being calculated after taking up the heat from the heat sources. And the second variant is a forced convection, wherein we introduce a fan to the same case, and we only consider one set of inlets. In this case, I say these to be inlets because we assume air goes in through this and comes out through the other end. But in this case, we do not define inlet or outlet. We just say air could go in and out through the same phases. We would see this in detail during the live demonstration. Now, to go with the simulation specification. So we use a compressible flow which would account for density changes. So the open foam case has a compressible buoyant flow solver. Both natural convection and forced convection could be performed using this compressible flow solver. So the density changes are brought about by temperature and pressure differences. We perform a steady state analysis. So in general, there are two types. One is called the transient analysis and the other one is steady state. In the transient analysis, we also have the marching direction to be time. So the solution is being calculated in direction of time as well as along the domain, and we could see the temperature in the domain at each and every time instant. But in a steady state analysis, it shows the result at an infinite time. So after all the heat transfer taking place and the steady state has attained, we see the steady state result. But why do we use the steady state result? Because it is computationally less expensive, because the cross terms and higher order terms in the equations are being are either cancelled out or neglected in order to efficiently calculate them quickly. And then for turbulence modeling is completely a new webinar topic. So it is like the topic is so huge, and it has a lot of content to be discussed. So in short, we would be using the K omega SST model for this case, which accounts for turbulence at wall shear stress level. And some conditions which are given to it. We have the inlet temperature, as I told you earlier, and we have the heat source defined in terms of wall heat flux. We assume fixed temperatures to some other components because there are a lot of other components which could like give out small heat out of it. So we assume them to have some fixed temperature. And then a fan boundary condition for the forced convection case. And using these conditions, we study two different cases. And what are the outputs which we expect out of it? On the first note, it is going to be the flow and pressure distribution in the domain. And for heat transfer analysis, the important aspect would be the temperature distribution inside the domain, as well as the surface, the temperature on the surface of the components and the other walls. We could also check for hotspots and recirculation regions, and I would tell you how this affects the heat transfer phenomenon. Using SimScale Platform to simulate, as I told you earlier, it is a 3-step process, and now let us look into it quickly. So the first step is the CAD upload. So you do the CAD model in any of the CAD softwares and then import it directly into SimScale, and then you create a mesh and set up a simulation, and then look for post-processing and do some design changes if required in order to get the desired results. Now I'd quickly give you a live demonstration on the platform. And sorry for people who have attended this workshop or any other webinar session on our platform. This might be kind of repetitive, but this should help the new users to have a quick start. So I would just show you around how the platform works and so on. So in general, this is going to be the SimScale platform. It's and then you could create an account easily in like a couple of minutes. So once you have created an account, you could log in to see your dashboard, and this is where you would have all your projects, and here you can select the new project, give a title to your project, give a description about it, and then you can upload your CAD here. You also have the possibility to upload the CAD after you have created the project and in your project overview page. So now, as I told you during the beginning of the session, we have something called the public and private project. Please note that the public projects are available for everybody and the private projects only for the paying customers and users. So now, once you create a new project, usually this looks empty, but I would show you the completed project. As for this demonstration, you could upload your CAD using this option where you have many types of file formats in which you could upload the file. You also have the possibility to import the file directly from Onshape, and Onshape is, oh, I'm sorry guys, it's a typo. Onshape is the online cloud platform for creating a CAD model. Just like we have SimScale for carrying out your simulations, you have Onshape for your CAD model. So once you could sign in here and create a CAD model, and then you could directly import it from Onshape. Now we have the geometry. So this is for the natural convection case where we have the passive vents. These are the vents. So this is how the geometry looks like, and you have the two heat generating sources here as highlighted. And now we try to create a mesh. So how do we create a mesh? Just click on this particular geometry and click on new mesh. Once you do that, you already have something called a mesh generator. And then in this case, we try to generate the hexahedral meshes, which is hex dominant mesh, and we could choose one among these three. In principle, we would choose the parametric because parametric has the option to control the cell size wherever it is required. So we need a finer mesh at some regions. This could be controlled using the parametric options. So once you select the hex dominant parametric and click on save, you have a tree generated. And since we have already created the mesh, I would show a quick demonstration on this one. So once you do this, you already have the default settings. Basically, these are the advanced concepts. Now we go into this. We have something called the base mesh box. A base mesh box is one where we inside which we actually create the mesh. So this, we define this box, and then we have something called a material point. So we mention the dimensions of this box exactly outside this domain, or it can even be larger than the box, but please note that this could not be shorter than the actual dimension. Say for example, you cannot have it like, why not 0? So it's 0.4. So if you have something like this, then your mesh should be created only within this block. Even though your geometry is extending outside this, your mesh should be created only within this. So in order to avoid that, please create a bounding box which is larger than this. And material point is one which decides where your mesh is. So we have something called an internal mesh and an external mesh. External mesh for aerodynamic purposes usually. So in this case, you create the geometry, which is the car or an aeroplane, say for example, but you want the air domain, which is everything other than this car or the aeroplane. So what we do is we create the geometry, create a big bounding box, that is the base mesh box, and keep the material point anywhere outside the car or the aeroplane, so outside the solid body. Now this decides where our mesh should be created. So if you place it outside the car, the mesh should be created in the whole domain except the car, and the vice versa. If you place it inside, only the car domain would be meshed. So in this case, what we have, the geometry which we have is the air. So in principle, we have the electronic device here, and this is going to be the air domain. So we could in general create an internal mesh, and we give various surface refinements. So this is basically a surface refinement to the entire solid, in order that the measure automatically detects some small edges in order to refine the cells. And we give something called a feature refinement. Feature refinement is given to the edges. So if you have any edges, feature refinement is given to the edges, these edges, so that near the edges the cell sizes would be comparatively less, in order to better compute the solutions near the edges. And then we do a surface refinement for these two surfaces, where the heat transfer actually takes place, because the temperature solver is quite sensitive, so we need to have a finer refinement in those regions. Then we define something called the layers. Layers, okay. What are layers? Okay, we couldn't see it from here. We could basically see layers from, yes, when we do something like this, it's called a mesh clip. So 0.4, yes. So near the surfaces, we have something called the boundary layer effect or the wall effect. In order to capture these efficiently, the cells near the boundaries should be very thin or very small, compared to the other cells inside the geometry. So in order to achieve this, we use something called the layers. So as you can see here, we have layers in these surfaces. So these cells are smaller only in one direction compared to the other direction. This is achieved using the layers. And now once you define all of these, we select on the operation again and click on start operation. And then once the mesh operation is complete, now we go to the simulation designer tab. Please note, in the SimScale platform, there's one thing. For easy workflow, it is always top to bottom or left to right. So you go from top to bottom, filling out each and everything, or you go from left to right in order to achieve the results. So now once you're here, click on new simulation, and then set up a convective heat transfer simulation with turbulence. We discussed about all of these before this session. So now once we have created the simulation, I would show everything in the setup which has already been made. That would be much easier to show in general. So this is the model, and we choose a domain. So in this case, it is going to be active and passive, which are the two meshes which are already generated successfully. So I choose the passive convection type for this case. And we define something called the topological entity sets, which is like grouping the sets in order to define boundary conditions later on. So you just name them, which could be accessed later on easily. And now we define the gravity in the required direction. So this 9.81, in the negative y direction, so it is going to be minus 9.81. And now we select the material. We have a variety of materials in the SimScale default library, and you also have a different library for structures or solid materials and a separate one for fluid. And if you would like to use any of the custom material, you could just insert one and change the properties over here to have a custom material as well. You assign it to the region, and initial conditions are the ones which you say during the beginning of my simulation. These would be my settings of pressure, velocity, temperature, and so on. So basically temperature, I would assume that it is everything, the whole thing is at room temperature. So basically the device is not working at the moment. When it starts working and it starts generating heat, then we compute how the domain varies with respect to the temperature changes. Then the velocity, we assume a small velocity in the y direction. And why is it in y direction? Because due to buoyancy effects, we assume air would be going or moving towards, air plumes would be approaching towards the top of the wall as the hot air tends to rise higher. So we give a small velocity, very small velocity value just to aid this process. And the rest we define the default conditions. And now we define something called the inlet outlet boundary condition. Inlet outlet boundary condition is something like for these walls basically. So inlet outlet boundary condition is something like, we say air could go in and out of the same wall, but when it goes in at a particular temperature. When it comes out at the temperature after calculation with regard to the heat source and so on. And the total pressure in the system is this. We have inlet outlet conditions for everything, and regardless of what the initial conditions are, once the solver starts calculating, it takes into consideration these turbulence values into effect. And then we go into the wall conditions. We define the wall where we say it is no slip, so we have the boundary layer effects in this one. And temperature, it is set to 0 gradient, so there are no changes with respect to the wall. So it is like an adiabatic case. We define this to be at 600 watt per meter square, so the CPU to be at 600 watt per meter square. That is the watt. So in there is a term called the TDP, which is thermal dissipation power. According to this standards, we have the value of 0.5 watt for the CPU. That is the power which is generated. We calculate the surface area and then define the heat flux per surface area, so watt per meter square. And this is going to be 600 watt per meter square for a corresponding TDP of 0.5 watt. Similarly, we define it for the GPU as well, which is 500 watt per meter square. And the other components, small components, we assume them to be like at a slightly higher temperature, which is like 7 degrees relatively. This is much smaller. And now we do some numeric changes as well. This is in order to get some convergent solution. So based on the analysis type, OpenFOAM has many different types of solvers. So for every analysis type, we have multiple solvers for all the transport properties, starting from velocity, pressure, or enthalpy, and so on. In order to aid in better convergence, we use a particular numeric scheme, and this as well is a really big discussion, and you could see more information in our documentation page, and we would keep updating this page on numerics because this is really huge. And to be precise, we have not covered the entire numerics in our documentation as well. We would try to put even more information into this. We now say we run it for 5000 seconds with a time step of 1, and we just write two results states. So it is like I calculate this, I save the results at 2500 steps and also at the end for 5000 steps. And now once everything is done, we click on new simulation, and once this is created, click on start to start the operation. So I have already created the operation and have some results for you. So this is the case of passive convection. So you could see the heat generated from the CPU and the GPU, and because of this the hot air tends to rise. So the air which comes in, it tends to rise and then it keeps circulating. So this is a streamline of the air coming in, and on the walls we see the temperature changes which is experienced on the walls and walls of components as well as the external surface. Now this is a slice, so we see the region above the heat source, it is heated up completely, and you have a very high temperature over here. And all of this is because we just have air coming in and going at its own pace, and we do not like blow air into it to remove the heat from it. So we would have some quick discussion or quick look into the results later. Now I would show you the active case as well. So everything is going to be the case except that we have a space for the fan. So we would have a fan here which would in principle blow out air from the system to the external environment. We also have a mesh generated. All the settings are going to be the same, as in you have the surface refinement, feature refinement, and a surface refinement for the heat sources and a layer as well. So now for the simulation setup, until the boundary conditions, everything is going to be the same. So here comes the change. For the inlets, in general, okay, so this is assigned with the custom inlet, where we only say it is pressure inlet, and this time it is not pressure inlet outlet because we want air only to go into this one. And the top inlets, as I discussed earlier, it is completely not used in this particular simulation. So we have inlets in this case and we have outlet in this direction. And we could define a fan condition using a custom boundary condition of fan pressure. So I would show you a forum post where you have a short description about this. So basically this is how a fan curve works. So from the fan curve, where you have the volume flow rate and the pressure difference as the x and y axis respectively. So these values could be input as a table, and I could show you here. So this input would decide the characteristics of a fan. So you have the volume flow rates and the corresponding pressure differences which the fan would have, and the fan would work according to this fan curve which has been defined to it. And we define the direction to be out because it's going to be an outflow where the fan tries to remove the air from the domain. Everything else is going to be the same, and we run the simulation the same way. For the post processing, now you could see the airflow in here. So the air flows from the inlet to the outlet, and here in the temperature domain you could see the previous case it was around 380 Kelvin, and now in this case the highest temperature is of order of 325 Kelvin, which is like much lesser. This is because of the reason that when we make a forced convection, in this scenario, like the air tries to remove all the heat from the heat sources. I could also show you some cross-section view of the air. So in the previous case, you could see everything was red in the cross section, but here you see the heat rises up, but the air which comes from here tries to remove the heat to the fan boundary, and you do not see many hot region over this here because all the heat is being removed by the fan. And a slice in the other direction now. So this is how it goes. You could now visualize how this works. And for the results, we could quickly go through the results. So this is the case for natural convection, where you have the hot region at 383 Kelvin maximum temperature, and the average temperature on the CPU is going to be 350 Kelvin, and on the GPU 331 Kelvin. On the other hand, for the second variant with forced convection, we see the average temperature on the CPU to be around 40 degrees Celsius, which is like 37 degrees Celsius lesser than what we see in the natural cooling. So this aids in, like, helps in safety of the device. And you could also see that there are no hotspots or regions of really high temperature in the forced convection case. And the hot air plumes which rise up, and you could see the average temperature is something around 310 Kelvin, but in the first convection case, like, the hot air is completely being removed from the system, so it is really less. You could hardly see any air plumes going up. This is a glyph which shows there are recirculation in the region. What happens when recirculation is there? So what happens is the air keeps circulating. So even if it's the hot air, it keeps circulating in the same region, and it stays inside the domain because of these recirculation regions, because of which the entire region gets to a higher temperature. And we would like to definitely avoid it, and this is the whole point of avoiding the recirculation regions and the hotspots. But in the second case, we avoid the recirculation regions by forcing in air in particular directions. We see that the velocity is going to be 0.12 meter per second to remove the heat, but in the forced convection case, it is going to be 2.9 meter per second, which is the desired one. Or it depends on the design as to which is the desired one. So you want more heat to be removed or less heat to be removed. It depends on the application. For most electronic applications, it is going to be remove as much heat possible. So in this case, it helps. And these are some fancy images of the streamlines, and you see for the passive convection case, the hot air is going up at the center, and it keeps recirculating as shown in the previous case. But in the next one, you could hardly see any particular recirculation patterns. It's just from the inlet to outlet. So I think we come to the end of it. This is to conclude. We now discussed two different types of design variants in which we see 40 to 48% surface temperature reduction in a case with forced convection, which would be the optimum one among the two. And we also see that CFD helps in better design for electronic cooling applications. So you could in general use any other electronic device to simulate and then find the optimum heat transfer which is required. That is the end of the session. So I would now look into any of the questions. Okay, so we have a question regarding the inlet outlet boundary condition. So how does this work? Excellent. I would quickly show you with the passive convection case. So what does the inlet outlet boundary condition do? Uh, in general, as I told you earlier, we have air going in and out of the same surfaces defined for boundary conditions. So the inlet goes in at no particular velocity defined, so it is just some arbitrary velocity which is around the in the atmosphere, and it goes at a particular temperature of 20 degrees Celsius as defined, which is the room temperature. And based on these conditions, the solver calculates the heat transfer, and then when it comes to the case of outlet, the outlet temperature, outlet velocity, and all other outlet values would be the calculated ones after the heat transfer takes place. So the outlet temperature should be a much higher value then, and the outlet velocity is dependent on how much heat the air takes up. So the more air it takes up, at least on the top winds, you could expect air coming out at a higher velocity. In comparison, this inlet case is just a pressure inlet and not a pressure inlet outlet case, so we only have air going into this one. Okay, and the next question. Okay, we have one regarding the advanced settings. So how do we decide on the advanced settings? This requires a little bit of knowledge on how the snappy hex mesh of OpenFOAM works. So basically, this is the OpenFOAM snappy hex mesh, and you have many properties. So to start with, the number of computing cores. The basic stereotypical notion would be that for any geometry, we choose the highest number of cores, and that would give us the result as soon as possible, which is not actually true. What happens is you always have an overhead. So on splitting up the incoming input into number of processes. So basically what happens is you give the information about the geometry and the mesh settings, and the mesher automatically splits it into various processes as defined here. So when I select 8 processes, it splits up into 8 different processes for computing the meshing process. What happens here is, like, if it is for a small geometry and then comparatively easier mesh settings where you expect lesser number of cells, then when you try to set it up on 32 cores, the overhead time, like experienced in splitting this into the number of cores and getting them back, would be higher than the actual time simulating or actual time creating the mesh. So on an average, I would say 50,000 elements for 1 or 2 cores would be optimum. In this case, maybe there are around, say, 1.5 to 2 million cells, for which 8 cores should be enough. So in general, you could take up 32 cores for mesh sizes which is greater than, say, 3 or 4 million. So anything greater than 4 million, I think you could directly 4 million as an expected, because you have many regions which are fine. Then you go with 32 cores, and you have the maximum locals and maximum global cells. This is with regard to refinement. So even if you refine, you want the maximum number of cells in that refined region to be this. And this is an important factor where it is the cells between levels. So cells between level, when we define it to be 3, how this works is, like, you have different levels. So as you had seen here, you had level 1, you had level 2, and level 3 refinements. I would say what these are. So basically, level 0 refinement is what you define inside the bounding box. So you draw the bounding box and you say in x direction, y direction, z direction, you split up into these many cells. So this is going to be level 0 refinement. So whatever the dimension is here, so between the maximum x and minus the minimum x, you find the difference, the distance between them, and you define this distance into 66 cells. So you have 66 cells in that particular direction. Similarly, you do it for y and z. And when you go for level 1 refinement, now you say in place of having one cell, I should have 3 cells. So that is going to be level 1 refinement. And level 2 refinement would be instead of like 3 power 2. So instead of having 3 cells in level 1, we have 9 cells in level 2. So that's how it goes on, and it keeps on going. So in general, we get the number of cells to be higher in wherever we require, or wherever the refinement is supposed to be. And this is one setting which we changed, which is the explicit and implicit feature snapping. So in this case, we set the explicit feature snapping to true, and we did this to make sure that the measure captures all the fine features. So you have, if you have many curvatures in your geometry, because we always have linear elements, and when there are many curvatures, the measure tries to snap the circular features using linear elements. So in order to get this done better, we use the explicit feature snapping. And the layer addition controls in general define the properties of how the layer should be. And I think you would see more of this with regard to OpenFOAM documentation or SimScale documentation. You can find more information into this in either one of these documentations. Okay, I see there are not many questions, as in terms of technical aspects. It is mostly regard to the platform, how things work, which we would be answering in the forum. So if there is going to be nothing else, I think I would wrap up this session. So thank you so much for joining us in these sessions of the thermal simulation. I hope you would have liked it, and please stay tuned for any other simulations and webinar sessions with SimScale. We would try to make things more interesting. Thank you and have a nice day. Bye.